When we think of high-performance computing, we tend to picture data living in a digital cloud. In reality, routing the world's information is a massive industrial operation built entirely on physical infrastructure. If you zoom in to the microscopic scale, this entire global industry relies on a brute force mechanical process. We are physically dragging billions of electrons through physical silicon barriers known as transistors. This is a thermal map showing the intense heat generated in the center of a standard processor die. Pushing matter through microscopic physical barriers creates severe electrical resistance. That resistance generates unruh friction. Unruh friction is the thermodynamic drag and heat loss created when particles are physically accelerated through a medium, and it acts as an absolute physical bottleneck on our calculation speeds. For decades, our solution was simply to make the transistors smaller, but we have now etched these pathways down to the atomic scale. We cannot pack them any tighter without the resulting heat completely melting the hardware. Engineers are bypassing this thermal wall entirely with the topological phononic computer. Instead of dragging physical electrons through a wire, this machine computes by routing localized acoustic waves through a crystal lattice, allowing it to process information with absolutely zero thermodynamic heat loss. The absolute limit of our computing speed is no longer tied to managing electricity. It relies on mastering frictionless geometry. To build this system, engineers start with a solid block of crystalline metamaterial. A metamaterial is an artificial structure engineered to control waves in ways not found in nature. Into this block, the system injects highly directed frictionless acoustic shear waves. There are no mechanical on and off switches here. A logic gate in this computer is a literal void, a highly specific Y-junction carved directly into the atomic lattice of the crystal. When two of these sound waves enter the junction perfectly in phase, they constructively interfere. Their combined kinetic energy creates a sharp pressure spike that routes smoothly down the output channel, giving us our binary 1. If those same two waves arrive at the intersection out of phase, they perfectly cancel each other out. The intersection instantly flatlines into a completely still vacuum, creating our binary 0. Multiply that single intersection by billions of precisely carved microscopic tunnels. Engineers can execute highly complex algorithms simply by choreographing exactly where and when these sound waves cross paths. We are taking the heavy lifting away from the physical matter. The empty geometric space is doing all the calculating. You might be wondering how a computer running entirely on delicate sound waves survives outside of a lab. Wouldn't the ambient heat of the room vibrate the crystal and scramble the data? Heat propagates through an environment as a longitudinal wave, meaning it expands and contracts outward in all directions. Our data, however, is encoded as a transverse shear wave, meaning the kinetic energy twists directionally along a very tight axis. Because these two wave shapes are mathematically orthogonal, they occupy the exact same physical space without interacting. The chaotic thermal noise washes right through the highly organized data stream without altering its trajectory. This exact property allows for topological chirality multiplexing. TCM is a transmission method where multiple independent data streams occupy the exact same physical space simultaneously. This is achieved by assigning each stream a completely different twisting direction, or winding number. Because these specifically shaped waves physically cannot destructively interfere with one another, engineers can stack multiple data streams into a single microscopic channel, achieving massive bandwidth in a tiny footprint while remaining totally immune to environmental heat. We now have a block of crystal performing perfect calculations using frictionless found. But how do we extract the final answer from that crystal and display it on a screen you can actually read? The system uses a transduction network interface at the edge of the processor. Transduction is the process of converting one form of energy into another. Here, the outer boundary of the metamaterial is etched with sharp, asymmetric, pre-stressed cavities. When the internal acoustic wave hits this edge, the physical tension forces the crystal to expel that kinetic energy as an electromagnetic shear wave. It instantly fires off a photon. It translates an internal acoustic calculation perfectly into external light. This allows the processor to plug directly into our existing fiber optic networks and traditional monitors. Instead of relying on a massive, red-hot silicon core demanding gallons of industrial liquid cooling, the exact same computational workload is handled by a silent, room-temperature block of glass. We don't need to force electricity through microscopic physical barriers to calculate the future. We can execute pure logic simply by sculpting the empty space it travels through.